Okay, so I kind of lied in the previous video, but you know what? I don't care because I like lying. I'm a rebel. So you better watch out for me. Who knows when I'm telling you the truth? So always question what comes out of my mouth because you never know if I'm playing a politician or not. I could just be telling you what you want to hear this entire time and not what's really actually accurate. Okay, so what did I lie about? What did I actually make that horrible sin with? And the issue was I oversimplified the lab a little bit. So in the previous video, I told you that you really only have to run 2 samples, right? Or that you really only have to do a sample and you look at the refractive index and you figure out what kind of compound that you have. And then you run it on the automated instrument and you look at these 2 numbers to make sure that they're the same. And then you'll pick out what your unknown is from a lineup. Well, there's actually another part to that lab that I didn't tell you about that I forgot until I looked at the lab sheet myself. Okay, so what does that mean? What more work do I have? Well, what I've described in the previous video was running refractive indexes for what we call pure substances. And you're going to read a pure substance and determine what that unknown is based on a chart. Okay, the second part to the lab is realizing that refractive index can be used to also calculate mixture composition. So we will have a series of mixtures for you to run. And these mixtures you will run on a refractive index instrument and report to us the concentration or the percent makeup of that 2-component species. Okay, so how do we do that? Well, we do that with an equation. So let's say that I'm given A and I'm giving a B. An A component and a B component. These are 2 different compounds. Now, what those compounds are, we'll tell you the day of, because whatever we feel like making, that's what we'll do. But this is my component A and component B. In order to analyze a mixture, I need an equation. Okay, so what I do is that once I figure out what my component A is, I run this on refractive index and I get a number. And then I take my component B, I run that on refractive index and I get a number. These are the pure compounds that I'm reading. I then take the mixture. So I'm going to put this as AB mix. And I put that on the refractive index and I get a number. Okay, so this is the unknown. But it's an unknown mixture in this case for part 2 of the lab. So what I do is that I come over to the side and I need to use an equation. And the equation says I can calculate the percentage of my A component. Whatever I want to put A as, that's what I put A as. Doesn't matter how I set the problem up, as long as I keep track of it. In order to calculate the percentage of that component, I'm going to take the refractive index of the mixture and I'm going to subtract the refractive index of my B component. Whatever I've decided to label B as, that's what I've labeled B as. And then I'm going to divide it by the refractive index of my A component minus the refractive index of my B component. And then because this is a percentage, I'm going to take that ratio and multiply by 100. And that will give me the percent of A that's in my sample. All right, so let's come over here to the side and let's do an example of this. So let's say that my component A is toluene. And let's say that my component B is something called cyclohexane. And this AB mixture has an unknown amount of toluene and an unknown amount of cyclohexane in it. And it's my job to figure out how much toluene is there and how much cyclohexane is there. So what I will do in the very beginning is that I will take pure toluene, that's all that there is toluene, and I put this onto the refractive index instrument. And when I put that on the refractive index instrument, I read it. And I get a value of 1.4970. I then will take pure cyclohexane because I know that these are my two components in the mixture. I take pure cyclohexane, I run that on the refractive index, and I get a value of 1.4266. And then I will take the mixture that has an unknown amount of toluene and an unknown amount of cyclohexane, and I read that on the refractive index. And what I will get there is, let's say, a 1.4562. And it's up to me to figure out how much toluene and how much cyclohexane is there. So I use this equation to help me out. Okay, so here's the thing. As long as you keep your numbers straight, you know that you're done. And you could do this same setup a different way than somebody else, but you get the same answer as long as you follow through with the steps. So look at what I've done here. I have just randomly assigned toluene as the A piece, and I've randomly assigned cyclohexane as the B piece. Okay. I could have switched these around. As long as I know which one's A and which one's B, it's okay. As long as the numbers go into the right spot in the equation, it's okay. You'll get the same answer in the very end. It doesn't matter. Okay, so my percent of A. Well, I'm going to rewrite this, and I'm going to say my percent of toluene, because I randomly said A represents toluene here. Okay, so percent of toluene is equal to refractive. By the way, anytime I say toluene, I don't know if you have watched The Nightmare Before Christmas, a wonderful Tim Burton animation. There's a song in there, toluene, toluene. Well, it's really Halloween, Halloween. So I always think of that song when I do that. I know it's kind of weird and strange, but if you've never watched Nightmare Before Christmas, do it. It's a cult classic. All right, so percent of toluene equals refractive index of the mixture. Well, my mixture here is 1.4562. And I'm going to subtract the refractive index of the piece that I labeled as B. So here's B, that represents cyclohexane. That is a 1.4266. And then I divide that by the refractive index of the piece that I labeled as A. Well, that was toluene. So 1.4970 minus my refractive index of the piece that I labeled as B, which was cyclohexane, and that's 1.4266. All right, so I come down to the side and I just clean up this calculation a little bit, and I'll bring the calculator up so you can see it in real time. 1.4562 minus 1.4266 gives me 0.0296. Okay, so 0.0296 divided by, well, I do the bottom, 1.4970 minus 1.4266 is 0704. Okay, I can't forget to multiply by 100 over here. So then I take those two numbers, 0.0296, and I divide it by 0.0704, and then I multiply by a 100, and that gives me 42.0%. Be careful with significant figures here. Okay, I subtracted these numbers on top, 4 after the decimal, 4 after the decimal, 4 after the decimal. I subtracted the numbers on the bottom, 4 after the decimal, 4 after the decimal, 4 after the decimal. When I do that, I'm dividing these two numbers now. There's 3 sig figs on top, 3 sig figs on the bottom, so my answer should have 3 sig figs, and that equates to 42.0%. So 42.0% is the concentration of toluene. All right, well, how do I calculate the concentration of my other component? And let's say that that's cyclohexane. Well, I assume two component only. So once I know one, what's the remaining piece of the pie, right? So I'm going to take 100, because in totality it's 100%, minus 42%, and that will give me what I should be looking at as far as the other half of the story. So the percent of cyclohexane is going to be 57.95%, or really 58%. And that tells me the percentage of my two component mixture. And that is how we use that equation to solve for that. What will happen in the lab is that we will give you a mixture, but we will give you 4 of these to do. You will have to analyze all 4. Okay? So what will happen in the lab is that number 1, you will have an unknown that you will identify from a chart. And number 2, you will then have 2 pures that you will run, that we have used these to make the mixes with. And then you will have 4 mixes that you will have to analyze as well. So a total of 6 samples in the second part of this refractive index lab. Now, what if I'm given a question to look up refractive index? Where do I find that information from? Well, you can go to somewhere like Wikipedia and you can type in toluene or cyclohexane. This is cyclohexane here. And if I scroll down to the side and look at the properties of cyclohexane, I see a couple of different things here that kind of go by physical properties, and one of these that I will see is refractive index, and refractive index is listed 1.42662. So they've went a little further than what our Abe refractometer can provide. They've went to 5 decimals instead of 4. Notice how they've labeled refractive index. It's N sub D, and I want to talk about that value for a minute. N sub D is the way that they represent refractive index in a reference textbook. And this reference textbook could be something like the Merck. So when I open the Merck reference book up and I find cyclohexane, they will abbreviate refractive index with a N value with a small d down below. The small d is going to represent sodium D lamp. It's very important that we give this sample only 1 nanometer of light, one specific nanometer of light to shine into. And this light is from a sodium D lamp. So this takes out a variable of the equation for us. We have a light source that we're calling the lamp. That lamp is only providing 1 nanometer of a specific wavelength of light. Now, what does that really mean? Well, think about your colors for a minute, your Roy G. Biv rainbow. The reason that you see different colors is because they're different wavelengths. So red has a different wavelength than green, which has a different wavelength than blue. And because they're all different wavelengths, your eyes interpret them in a different way, and they come to you in your head as a color. Well, we don't want any of that to happen. We don't want this mixture of all of these different wavelengths to be shining into the sample. So we only use a light source that's providing 1 specific nanometer or wavelength of light. And that's the sodium D lamp, and that's why the D is down below. Sometimes you'll also see a number up here at the very top, and that number, if it's listed, is the temperature. So 20 degrees or 25 degrees or 30 degrees, what is the temperature of the sample that you ran? There's a proper temperature correction that we should do with the refractive index reads, but we won't go through that now. We'll wait until later on to look at that temperature correction because that's just too much. So what we'll do is we'll learn how to read the instrument or use the instrument, learn how to read samples with refractive index, and then we'll take this data and look at some charts and some calculations with it. But there is a proper way to correct for the temperature if it's not at 20 or 25 degrees. So that's the story with the lab. Have fun, and I'll see you there.